Wow, it's so hot in this theoretically perfect black body car. Oh, what should I do?
You should have worn white, loser.
What would that do?
Let me tell you about a little thing called radiative heat transfer.
Okay.
Radiative heat transfer is when an object is exposed to electromagnetic waves. Some of the energy from these electromagnetic waves is converted to heat, increasing the temperature of the object.
So, why would it matter if I wear white?
Properties of the material affect how much energy is transferred to heat. A perfect black body is an ideal absorber and ideal emitter, so it converts all of its energy to heat.
Oh, okay.
And by the way, for materials that are not black bodies, aka real bodies, not all energy is absorbed and converted to heat. Some of them are transmitted and reflected.
Wait, transmitted and reflected? I'm not really sure that I get it.
Why don't we give you a demonstration?
Together we are G, the irradiance, the radiation that reaches the object.
Okay, let's see some IDs. Don't you know who I am? I'm reflectivity times G. I can't let you in. Reflectivity dictates what part of G is reflected off the surface.
What? That's
Get out!
outrageous.
I'm transmittance times G. I'm just passing through.
Transmittance, huh? That's the part of G that dictates what part of the light goes through the object.
Exactly.
All right, you can go in, but pass right through. Make sure you leave right away.
I'll surely do that.
I'm absorbance times G. I'm gonna say it all night long.
Oh, absorbance, huh? You're how much of the light actually stays inside the object. I see. Come right in.
Okay, I think I get it, but now I kind of want to try it out for myself. Will you guys help me run an experiment?
Yeah.
Absolutely.
And just one quick question. How did you get into my car? I hope they still help me.
I know, right? Like, wait, why wasn't I given any lunch?
The purpose of this project is to investigate the effect of radiation on colors. Radiative heat flux equals to emissivity times Boltzmann constant times temperature raised to the fourth power. Radiative heat flux is affected by temperature. Therefore, our first goal of this demonstration is to measure the final temperature of differently colored solutions. For the purposes of this experiment, we're assuming that our solutions are black bodies. Black bodies are those that are classified as ideal absorbers, ideal emitters, and diffuse emitters.
For this experiment, we expect darker colors to absorb heat more efficiently than lighter colors. To begin, we measured 40 milliliters of isopropyl alcohol in a clear glass. Then we recorded the initial temperature of the alcohol before placing it under a 50-watt heat lamp that had been preheated for 5 minutes. We left the IPA under the lamp for 5 minutes before recording the final temperature. Now that our control is out of the way, we have to repeat this procedure 5 more times for our colored alcohols: light red, light blue, dark blue, and black. After 2 separate trials, we recorded all of the data in a table and saw that our hypothesis was correct. The black alcohol had the greatest overall temperature increase, followed by the dark red, dark blue, and light red. Light blue alcohol and clear alcohol both showed the same average temperature increase, however, which was unexpected but did not disprove our hypothesis.
Another parameter that we need to use to calculate the radiative heat flux is emissivity, as shown in the equation. Although we could look up emissivity values on Google and use those as estimates, those values vary quite a bit based on the color shade. Therefore, to be more accurate, we will acquire our data by using a UV visible spectrophotometer. Essentially, this is a device that can measure light absorption. By using the UV vis to acquire absorbance values for our liquid solutions, and while assuming that our liquids are in thermal equilibrium at room temperature, we can then use Kirchhoff's law to correlate absorbance with emissivity. These are directly proportional because absorbance and absorptivity are also directly proportional.
Now let's have some fun. Put on our lab coat, say hello to our sun, and make our solutions again. Let's put them into cuvettes now, and now we can load our machine with the cuvettes. Make sure we measure absorbance, and now we can start the machine. So while we're waiting for our values, we can do something important, like study for mass and heat. So, after collecting all of our data, I compiled all of it into an Excel sheet and made a graph. As expected, our darker colors actually had much greater absorbance values than our lighter colors. Surprisingly, we actually saw the exact same trend as we did in our first experiment. Black had the highest absorbance value, followed by dark red, dark blue, light red, light blue, and then finally the clear IPA.
In conclusion, both experiments were successful. The first experiment, which evaluated radiative heat transfer on differently colored liquids, revealed that darker liquids exhibit a larger rise in temperature than lighter liquids in the same amount of time. The second experiment, which utilized UV-Vis to measure the absorbances of differently colored liquids, yielded higher absorbance values for dark liquids and lower absorbance values for light liquids. These experiments together, along with the radiation balance equation, confirm our hypothesis that darker colored liquids exhibit higher rates of radiative heat transfer than lighter colored liquids.